Summary on second chapter, electrostatic potential and capacitors. Now, potential. Electrostatic potential is defined as the ratio of work done to charge. So it is W by Q, joule per coulomb or volt. So work done is potential into charge. Work done is potential into charge. This is true when one of the reference points is at infinity. Instead of that, if two points are considered where potentials are V and V, then work done is given by, this is final and this is initial. Suppose this is initial point and this is final point. Then potential at this point Vf, potential at this point Vi. What is the work done in moving this charge from initial to final means final potential minus initial potential into charge. So that gives a measure of work done. So this we will be using in MCQ. Now, potential due to point charge. Potential due to point charge. Because of this charge, capital Q, potential at this point P is given by potential equal to constant charge by distance. So this is the distance. Okay. So potential is inversely proportional to 1 by R. Electric field at this point due to this charge, electric field equal to constant Q by R square. This is R square, distance square. So electric field is inversely proportional to square of the distance. So using these two, we can draw a graph of electric field and potential versus distance. See, potential is inversely proportional to distance. Means potential decreases like this with respect to distance. And then electric field inversely proportional to square of the distance. Square of the distance means it falls sharply. So this is 1 by R square. So this is 1 by R square. And this is 1 by R. Potential due to dipole. In first chapter we have seen electric field due to a dipole. Now potential due to a dipole. First the general expression, after that two special cases. Potential at a point due to a dipole. This is a dipole, minus Q plus Q. This is some arbitrary point P. Direction of dipole moment is from minus Q to plus Q. So this is the direction of dipole moment P cap. This is the position vector R cap. So angle between these two is theta. And electric potential at this point is given by V equal to constant P cos theta by R square. So potential is inversely proportional to R square. This is due to a dipole. Due to a point charge, it is 1 by R. But here it is 1 by R square. Okay. Now, special case. If theta equal to 0 degree. Theta equal to 0 degree means this is the dipole. Minus Q plus Q. Minus Q and this is plus Q. If point P is on the axis of the dipole like this. This is point P. Then from the center of the dipole to point P. This is the position vector. This makes an angle 0 degree with respect to dipole moment. So this is the dipole moment, isn't it? So this is the dipole moment. See, dipole moment is from minus q to plus q. If point P is here, this is the direction of position vector and angle between them is 0. In this case, substitute 0 here. Then potential at this point is constant P by r square. Cos 0 is 1. Now, if theta equal to 180 degree, 180 degree means this point should be on the other side. This is the dipole. Minus q plus q, center of the dipole. And here lies the point. This is point P. So from the center of the dipole to point P, this is the position vector. So this is r cap. And then dipole moment is from minus q to plus q. This is the direction of dipole moment. See, these two are in opposite directions. Opposite directions means theta is 180. Cos 180 is minus 1. Potential is constant minus P by r square. Minus P by r square. Now understand the climax of this topic. This point is closer to positive charge than negative charge. Therefore, influence of positive charge is more. That is why this equation is with positive sign. Whereas in this case, this point is closer to negative charge than the positive charge. This point is closer to negative charge means negative charge influence is more. That's why this potential is with negative charge, negative sign. Which is the third special case. If theta is 90 degree, if theta equal to 90 degree, so this is the dipole, minus q and this is plus q, center of the dipole. Then from the center to point P, this point P is on the equatorial plane, then this is the position vector, unit vector of the position vector r cap, and this is the direction of dipole moment. Angle between these two is 90. Cos 90 is 0. So potential at this point is 0. Potential equal to 0. Now potential equal to 0 means how you should visualize? Potential due to positive charge, say plus 20 volt. Potential due to negative charge, minus 20 volt. Resultant potential is 0. A uniform electric field exists along positive x-axis. The work done in moving 0.5 through a distance 2 meter along a direction making an angle 60 degree with x-axis is 10 joule. Then the magnitude of electric field is, okay, there is electric field along x-axis. So this is x-axis electric field. Displacement makes an angle 60 degree. Fine. So work done equal to force dot displacement. Fine. Which is equal to F S cos theta. This electric field is, or this force is charge times electric field. Displacement cos theta, cos 60 is half. So this is the work done. Work done is 10 joule, charge is 0.5, just check, charge is 0.5, electric field wanted, displacement is 2 meter, displacement is 2 meter and this is half. So 2.5 is 1, 2, 10 is 20. So electric field equal to 20. Electric field is 20. Volt per meter. There are two units, right? One is Newton per coulomb. Second is volt per meter. Volt per meter. Newton per coulomb. So here Newton per coulomb is mentioned. What is the electric potential at a distance 9 centimeter from 3 nanocoulomb? It's due to a point charge. So potential due to point charge is constant Q by R. Constant is 9 10 to the power of 9. Charge 3 nano minus 9 by distance is 9 centi. Centi is 10 to the power of minus 2. Say 9 get cancels. 3 minus 9 plus 9. 10 to the power of minus 9 plus 9. So this goes to numerator. So we are left with 3 and this is 300 volt. See, if you neglect this centimeter, then you will get only 3. 3 is also there in one of the options. So you should be careful, okay? So such small conversions will be there. The electric field and the potential of an electric dipole. First electric field, isn't it? Electric field due to dipole is 1 by R cube. Electric field. And potential is 1 by R square. 1 by R cube and 1 by R square. If you don't consider this, then you are in trouble. What is the common mistake? Electric field is 1 by R square and electric potential is 1 by R. So this is the common mistake. Is it there? Yes, it is here. N identical droplets are charged to V volt each. If they coalesce to form a single drop, then potential will be. So potential equal to constant Q by R. These are the small droplets. These are the small droplets. Radius of this droplet is R and charge is Q. Radius is R and charge is Q. Okay, fine. They combine to form a bigger drop. Radius of bigger drop is capital R and radius of bigger drop is equal to cube root of n times radius of smaller. We will see this. If charge on each is Q, then total charge on this is n times Q. Hope you understood. Charge on each droplet is Q. They combine to form a bigger drop. So total charge is n times Q. Say potential due to bigger drop, smaller charge on this bigger drop n times Q by radius of the bigger drop is R and this radius is n to the power of 1 by 3 into R. And this Q by R, please understand, this Q by R gives smaller potential. So potential due to bigger drop is equal to n by n to the power of 1 by 3 is 2 by 3 into V, potential due to smaller drop. Okay. So this is n by n to the power of 1 by 3. N by n to the power of 1 by 3, which is n 1 minus 1 by 3. N 2 by 3. You understood this. Now let me explain why is it so. Let me explain why this is so. Okay. So in such problems, you have to take care of radius of the bigger drop. N times volume of smaller droplets. N times volume of smaller droplets. N times volume of smaller droplet is 4 by 3 pi R cube equal to volume of bigger drop. Volume of bigger drop is 4 by 3 pi R cube. So what are we assuming here? When these droplets combine, their total volume remains same. Therefore, observe 4 by 3 get cancels. Radius of bigger equal to, take cube root, R cube becomes R. This is cube root of n. See, radius of bigger drop is cube root of n times radius of smaller drop. Cube root of n times radius of smaller drop. Now, Just follow what I say. These are smaller droplets. 27 such smaller droplets are combined to form a bigger drop. What is the radius of the bigger drop? Radius of bigger drop is, what is cube root of 27? 3. So it is 3 times radius of smaller drop. One more. There are 1000 small droplets. 1000, okay? 1000 smaller droplets. They combine to form a bigger drop. What's the radius of the bigger drop? Radius of the bigger drop is cube root of 1000 is 10. So 10 times radius of smaller drop. So you should be fast enough to find this. Thereby you can find out potential, and that potential is 2 by 3 times V. Equipotential surfaces. Equipotential surface means potential should be constant at every point. Potential should be constant at every point. On an equipotential surface, potential difference between any 2 points is 0. On an equipotential surface, work done in moving a charge from one point to another point is 0. So these are the conditions for an equipotential surface. Now, using equipotential surfaces, we can derive that electric field equal to minus dV by dr. If it is along x-axis, then electric field equal to minus dV by dx, y-axis dy, z-axis dz. Look at the beauty of this equation. This is an operator. This is called a gradient operator. Gradient. When a gradient operator operates on a scalar quantity, we get a vector quantity. But we have not used vector notation, isn't it? So this is there in our syllabus. What's the vector form of this means? E equal to minus dV by dx. If you write vector sign here, then it should be I cap. With negative sign, differentiate the equation of potential with respect to x, and that gives electric field E. So let us see how to use this equation. The electric potential at any point x, y, z in meters, okay, is given by 3x square. So potential equal to 3x square. The electric field at this point, okay. So first E equal to minus dV by dx. So let us differentiate this with respect to x. 3 into 2, 6 with negative sign, 6x, isn't it? It's simple. Differentiate this with respect to x. Now there is only x term. So substitute x equal to 2. Then minus 6 into 2 equal to minus 12. Minus 12. So this is minus 12 volt per meter. Since it is electric field, volt per meter. Negative sign means it is on negative x-axis. Electric field is on negative x-axis. So in such problems, you have to take care of this negative sign. That negative sign describes the direction of electric field. Now, potential energy. Electrostatic potential is work done per charge, but now potential energy. So there are many equations. Give attention to these equations. Potential energy of a point charge. Potential energy of a point charge. Not defined. Let me denote potential energy by U. Not defined. Not defined means we write infinity, isn't it? So infinity, not defined. Potential energy of 2 point charges. Potential energy of 2 point charges. This is Q1 and this is Q2 separated by distance R. This is potential energy of a point charge. Due to point charge, potential energy not defined. Due to two charges, potential energy equal to constant Q1, Q2 by R. Now, if there is no second charge, means this becomes 0. Q2 is 0. And then R is 0. What is 0 by 0? Not defined. That is why if there is no second charge, because of only one charge, potential energy is not defined. For two charges, it is constant Q1, Q2 by R. And this constant is 1 by 4 pi epsilon naught. Okay. K equal to 1 by 4 pi epsilon naught. Now, because of three charges, first, second, third, Q1, Q2, Q3. Distances R1, R2, R3. Potential energy due to 3 point charges constant into, because of these two charges, Q1, Q2 by R1, Q1, Q2 by R1 plus Q2, Q3 by R2, Q2, Q3 by R2 plus Q1, Q3 by R3, Q1, Q3 by R3. So this is the expression for potential energy of 3 point charges. Potential energy of 3 point charges. Now, if this is an electric field, E, and in this electric field, there is a charge, and potential at that point is V. Potential at that point is V, and we are keeping a charge. Then that charge has potential energy. So potential energy of a charge in electric field is V times Q. Now, this is uniform electric field. So there is a charge Q1 at potential V1. There is another charge Q2 at potential V2. Distance between these two is R. What's the potential energy of this system? So potential energy equal to, say, because of this charge at this potential, V1 into Q1 plus this charge in this potential, Q2 into V2 plus, forget electric field, okay? Forget electric field. Consider two charges. Because of two charges, potential energy is constant Q1, Q2 by R, distance between the charges. So this is due to this potential, this is due to this potential. This is, by neglecting electric field, there is one more potential energy. That potential energy is potential energy due to 2 point charges. So sum of these three gives the net potential, electric potential energy, not just potential, electric potential energy. So these are few equations. Let us revise all these equations when we are solving problems. If problems on these appear, then let me revise one more time, okay? The mutual electrostatic potential energy, it is not force, potential energy, between two protons which are at a distance 9 × 10⁻⁻15 meter in that nucleus. So if this distance is there, means the proton should be inside a nucleus. They are not free protons. So there are two protons, Q1 and Q2. Q1 and Q2. Both are protons. Distance is this. So potential energy is given by constant Q by R. Constant is 9 × 10⁻⁹. Charges 1.6 × 10⁻⁻19. 1.6 × 10⁻⁻19 by distance is 9 × 10⁻⁻15. See, we have to solve such problems. We have to simplify, but without calculator and logbook. Very easy to solve. And before solving this, you just go through this 1.56, 5.5, 2.56, 4.5 distinct values. They are not very close to each other, isn't it? Then it will be easier to solve. See, this 9 get cancels with this 9. Remaining is 1.6 into 1.6, 2.56, 16 square. 2.56 means it is here. If this is not the answer for the product of these two, then other three cannot be the answers. Then at that case, or in that case, you will get a grace mark. See, we are not checking this. You don't have to worry about this as long as these are distinct values. Okay. So just go through 1.6 into 1.6, 2.54, 16 square, 256. In the case of dielectrics, nothing but insulators, there is a linear dielectric. What is the meaning of linear dielectric? Means dielectric polarization is equal to epsilon naught into chi times electric field. This is absolute permittivity of free space. This is electric susceptibility. Electric susceptibility. Susceptibility. If dielectric polarization is directly proportional to electric field, then such dielectrics are called linear dielectrics. So this equation is mentioned in NCERT book. Now, what is dielectric polarization? This is not dipole moment. Okay. Dielectric polarization is net dipole moment per unit volume. Net dipole moment per unit volume. Dipole moment is charge, coulomb, distance, meter, by volume is meter cube, volume of the specimen, equal to coulomb per meter square. Dielectric polarization. Since it is mentioned in NCERT book, let us just go through once, at least once. Okay. Capacitors. Capacitors are used to store charge. So it is used to block DC, it is used to block noise. Let us read that or go through those two topics in 14th chapter. Okay. So in this context, in this chapter, second chapter, capacitors are used to store charge, electrical energy. Q equal to CV. Q equal to CV. Q equal to CV. Basic equation. Because of this, capacitance of a spherical conductor is 4 pi epsilon naught r. If this is a sphere, spherical conductor of radius r, and there is charge, the sphere can hold some charge. Means what is the capacity of the conductor? Capacitance of the conductor. Capacitance of this spherical conductor is constant into r. So you have to concentrate on this, is proportional to r. Capacitance of a spherical conductor is directly proportional to radius. As radius increases, size also increases, capacity increases. Capacity to hold charge increases. So this is the basic equation, Q equal to CV, isn't it? Fine. Now, capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor. If this is a capacitor, two plates, then there is air medium between the plates, then capacitance of capacitor with air medium is given by epsilon naught A by D. Area of each plate, distance between the plates, and epsilon naught is a constant. Now, if the capacitors are filled with, if plates, the gap between the plates is filled with a suitable dielectric medium of dielectric constant K or epsilon R, then this capacitance is capacitance with medium equal to epsilon naught epsilon r a by d. See, epsilon naught a by d. This is epsilon naught epsilon r a by d. So using these two, we can say that epsilon r is the ratio of capacitance of a parallel plate capacitor with dielectric medium to capacitance of a parallel plate capacitor with air. Recall epsilon r. Epsilon r is force between two charges in air by force between two charges in a medium, equal to, in terms of electric field in air by electric field in medium, equal to, in terms of potential in air by potential in medium, in terms of capacitance. Epsilon r is capacitance in medium by capacitance in air. See, air by medium, medium by air. So this is epsilon r, relative permittivity or dielectric constant. They are one and the same. Parallel plate capacitor, spherical conductor. Capacitance of a spherical conductor, short put like. In a parallel plate capacitor, if the intervening medium of permittivity epsilon between the plates is replaced by another medium of permittivity 2E, then its capacitance gets doubled, because capacitance with medium is epsilon naught epsilon r a by d, isn't it? In the first case, it is with epsilon. In the second case, it is with 2 times. If it is with 2 times, then capacitance also becomes 2 times. So capacitance with medium is equal to 2 times capacitance with medium. This is due to epsilon. This is due to 2 epsilon. Combination of capacitors. First series and then parallel. Students, just pay attention to those minute details. Okay. In series combination, first capacitor, second capacitor, third capacitor, C1, C2, C3. In series combination, potential differences are different, V1, V2, V3, whereas charge in each capacitor is same. If charge in the first is Q, charge in the second is also Q, charge in the third is also Q. So here 1 by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3. And then if all the values are equal, first, second, third, C, C, C. What's the equivalent capacitance means? Cs equal to each capacitor by, count the number of capacitors, 3. So divide this by 3. In general, if n capacitors are in series, then Cs equal to C by n. Now, one more detail. If capacitors are in series, then the equivalent capacitance, this capacitance is always smaller than the smallest. For example, first capacitor, second, third. Okay. This is 6 nanofarad. This is 3 nanofarad. This is 2 nanofarad. After solving this, the Cs turns out to be 6, 3 gives 2, 2, 2 gives 1 nanofarad. Students, you can find combination of capacitors in different configurations in one of the videos. Please check that also. Okay. So 6, 3 gives 2, 2, 2 gives 1. Look at this 1. 1 is smaller than the smallest. Among these three, this is the smallest. This is even smaller than the smallest. That is the meaning. In series combination, the effective capacitance is smaller than the smallest. In series combination, charge is same in all the capacitors, and total potential equal to V1 plus V2 plus V3. V1 plus V2 plus V3. This is the total potential. Now, parallel combination. Parallel combination is easy, isn't it? C1, C2, and then this is C3. These three capacitors are in parallel. C1, C2, and then C3. So C parallel is given by C1 plus C2 plus C3. Now, if they are of equal values, C, C, and then C. C, C, C. Then C parallel equivalent capacitance is 3 times C. There are 3 capacitors, therefore 3 times C. C plus C plus C is 3C. In general, for n capacitors, n times C. And here, this capacitance is always greater than the greatest. Example, first, second, third. So these capacitors are in parallel, isn't it? 1 nanofarad, 2 nanofarad, 3 nanofarad. 1 plus 2 plus 3 is 6 nanofarad is the CP. This 6 is greater than the greatest. This is the greatest, and this is greater than the greatest. So in series, smaller than the smallest. In parallel, greater than the greatest. And in the case of parallel combination, potential difference remains same. If potential difference across first capacitor is 4 volt, potential difference across second is 4, across third is also 4. But total charge equal to Q1 plus Q2 plus Q3. Charge in this plus charge in this plus charge in this is total charge Q. So this is with respect to parallel combination. Of course, let us discuss different combinations in one more video. Please also go through that. Okay. Give some time, copy all those diagrams, and then try and listen carefully what are the techniques used to solve those problems. Combination of capacitors. Three capacitors, 3, 6 and 6 are connected in series. 3, 6, 6 connected in series and connected across 120 volt. This is 120 volt. 6 nano, 6 nano, 3 nano farad. Potential difference in volt across 3 microfarad. Oh, all are in micro. This is in micro. 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 This is in micro. No issues. Potential difference. There are different methods to solve. Let us use one of the simplest method. 6 and 6 series means resultant of these two gives 3 micro. If this is 3 micro, this is 3 micro, equal, right? 3 and 3. Then potential difference across this is 60 volt and across this is also 60 volt. 120 volt, this is 60 volt and this potential difference is 60 volt. Anyway, we don't want across this, we want across this. So it is 60 volt. See, we have not used any of the equations. These two are in series, right? There are two identical capacitors in series. So 6 microfarad by 2 capacitors. That gives 3 microfarad. So this is 3, this is 3. Equal. 120 is divided equally. That's why we are getting 60. The equivalent capacitance between A and B. A, B. These two are in series. These two are in series gives 2. These two are in series gives 1. 2 and 1 parallel, it is 3. This is from one of the previous year question papers. Now, energy stored in a capacitor. Energy stored in a capacitor. There are 3 equations. Potential difference, charge, capacitance. In a problem, if you find potential difference and C, then try to pick half CV square. This is the expression for energy. In an equation, if you find Q and C, half Q square by C. Then in terms of potential and charge, half QV. So these are the equations. These are the equations for energy stored in a capacitor. So energy stored equal to half CV square equal to half Q square by C, also equal to half QV. These are the expressions. Last expression, energy density. If energy is stored in a capacitor, then what is the energy density? Expression for energy density. Let me make it clear. This is a parallel plate capacitor. Area of each plate is A. Distance between the plates is D. Then energy is given by half CV square. Energy is given by half CV square. Half C, capacitance. Capacitance of a parallel plate capacitor is epsilon naught A by D. And then expression for V, E equal to minus dV by negative potential gradient. Negative potential gradient is electric field, or potential difference by distance. V is the potential difference across the plates and D is distance between the plates. Therefore, V is E into D. So this is E into D square. Now simplify. Half D square by D is D. A. E square. This is epsilon naught. Left hand side is energy. Okay. Left hand side is energy. This is electric field. This is energy. Now energy by this gives volume. Area into thickness gives volume. So this gives volume. Bring this to the other side. Half epsilon naught E square. Isn't it something like half mv square? Just it looks like half mv square, but nothing to do with half mv square. Okay. So this is energy density. Energy by volume is energy density. So energy density is proportional to square of the electric field. If you know that energy density is proportional to square of the electric field, then you can use this equation to solve such questions. Energy density of a capacitor is 4 unit. What is the energy density? If electric field is doubled 2 times. 2 square is 4. So energy density becomes 4 times. Energy density of a capacitor is E. What is the energy density? If electric field is tripled, 3 square is 9. New energy density becomes 9 times. Okay. So it is important to know the equations. If you are not sure about this, energy density proportional to E square, then you will not have confidence to solve, isn't it? So what's the key technique or the big secret of solving MCQ means? It is to remember all the equations. If you know equations thoroughly, if you can pick equations means half the job is done. You will be confidently trying to attend the problem. Confidence matters. Okay. Yes. The amount of work done in increasing the voltage across the plates from 5 volt to 10 volt is W. Then the work done in increasing from 10 volt to 15 volt will be. Beautiful question. In mechanics also we will get questions like this. Energy in terms of velocity. 10 volt minus 5 volt is 5 volt. For 5 volt work done is W. 15 volt minus 10 volt 5 volt. So work done is W is the common mistake. Why means energy is not proportional to V square. Sorry, V. Energy is proportional to V square, isn't it? Because we are using energy equal to half C V square. Now let us understand 5 volt. This is 5 volt. This is 0. This is 10 volt. Let us find energy for 10 volt. 10 square minus energy for 5 volt. 5 square, because energy is proportional to V square. So 10 square minus 5 square is 75. For 75 difference, work done is W. Now 10 volt to 15 volt. 10 is here, 15 is here, 15 volt. What is 15 square? 15 square minus 10 square. 15 square is 225 minus 10 square is 100. Difference of these two is 125. See, if 75 difference corresponds to W, then 125 difference corresponds to W dash. 125, 75 to 125. 75 into 2 is 150. This is less than 150. So it should be less than 2. It should be less than 2. This is 1.67. Now, let us solve this in a different way using equation. See, work done is half C V square. Difference of these two. 10 square minus 5 square is W. Work done is W. W dash is half C. Final is 15. 10. 15 square minus 10 square. Divide one by the other. This get cancels with this. Numerator gives 75. Denominator gives 125. Therefore, W dash equal to W times 125 by 75. 25 3, 25 5. 5 by 3 is 1.67 times W. 1.67. What you should understand? You should not get into this trap. 5 to 10 volt W. 10 to 15 volt W. No, it is not W. It is 1.67. 1.67. Because energy is directly proportional to square of the voltage. Using this summary, let us solve other MCQ.